Hi guys, let's try one more problem. Two identical circular wires P and Q, each radius capital R and carrying current capital I, are kept in perpendicular planes such that they have a common center as shown in figure. Find the magnitude and the net magnetic field at the common center of the two loops. So this is the given diagram. So in this diagram, we need to find the magnetic field at the center. So since magnetic field is a vector, so first before trying to find the magnitude, let's try to find its resultant direction, because here two circular loops are there. Suppose if I make one loop, a loop which is in this direction, so this is P loop, this is the current direction. So if I curl my right hand fingers in the direction of current and the resultant thumb direction, so that is showing upward direction. So therefore the resultant magnetic field, so that is along in this direction. So this is the magnetic field due to P loop. And what about another loop, that is Skew loop? So if I draw one more loop at here, so in this loop the current is flowing in the counterclockwise direction. So if the current is flowing in the counterclockwise direction, what is the resultant magnetic field direction? So curl your fingers in the direction of magnetic field. So if I curl my fingers in the direction of magnetic field, so that is showing towards to my right side direction. So my thumb is showing towards right side direction. So that is the resultant magnetic field direction. Now if I combine these two, so if I draw that two separately, so this is, I can mention it here, the magnetic field due to Q loop. So the magnetic field due to Q loop is along in this direction. So this is magnetic field due to Q loop, and the magnetic field due to P loop, so that is along in this direction. So this is magnetic field due to P loop. Since these two are vectors, so there is resultant direction. So the resultant field direction is along in this direction. So this is the resultant of magnetic field due to both P and Q. So we need to find the resultant magnetic field by using a vector. So the resultant magnetic field B equal to under root of, or if you know that, R equal to, if A bar and B bar are two vectors, to find the resultant vector R equal to square root of A square plus B square. So this is the rule we were using to find the resultant vector by using triangle law of vector addition. So if we can use the same at here, so the resultant magnetic field B equal to, so the magnitude of magnetic field due to BQ, that is whole square, plus the magnitude of the magnetic field due to BP, that is whole square. So this is the resultant magnetic field direction. Now try to find the magnetic field magnitude. Since they both are having same radius and same current, therefore their magnitude is same. Suppose if I call that magnitude BQ equal to BP equal to some B naught, to do the simplification. Since they both are having same, Now the above expression changes. B equal to square root of B naught square plus B naught square. Usually write it here, I can substitute the magnitude of magnetic field formula, but that looks very big. So before that I want to just simplify that. So it becomes 2B naught square. If I simplify this becomes root 2 times B naught. So here we need to write the what is value of B naught. So the B naught value here we already having. The magnitude of magnetic field at a point. Suppose if I can take this. So this is the magnitude of the magnetic field. Here B naught equal to mu naught n I times A upon 2 of A square plus x square whole power 3 by 2. But here we are finding at center. So I can take x equal to 0. So but at center the x equal to 0, this formula will be changes as this formula, B equal to mu naught n I upon 2a. So this is the magnetic field at the center. The final result, the magnitude of magnetic field. The magnitude of magnetic field B equal to under root 2 times mu naught n I upon 2a. When we can do further simplification, those root 2 in 2 is root 2 times. Therefore B equal to mu naught n I upon root 2a. So here a is the radius of the loop. So this is how we need to find the magnitude of the magnetic field and the resultant direction. So again I am giving one suggestion. Before finding the magnitude, just figure it out what is the direction. So finally the magnitude of the magnetic field and the resultant direction, we got it. Let's try one more model problem. Two identical circular loops P and Q of radius small r and carrying current I and 2I respectively are lying in parallel planes such that they have a common axis. The direction of current in both the loops is clockwise as seen from O, which is equidistant from the both loops. Find the magnitude of the net magnetic field at point O. So given problem, two loops of equal radius of small r, the radius of loop is little r. But they both are having a common axis. So in the common axis, they both are separated at a distance of 2r. And current in the one loop is I and current in another loop is 2I, and direction of current is clockwise direction. And we need to find the magnitude of the magnetic field at a given point O. Suppose if I take this is a loop of P and this is Q. Before solving the magnitude of the magnetic field, we need to find the resultant direction of the magnetic field, because magnetic field is a vector. So sometimes we used to get the resultant of the two vectors. Now by using right hand thumb rule, so when it is moving in the clockwise direction, So clockwise direction, suppose if I take clockwise direction along in this direction, so this is the clockwise direction. They both are moving in the clockwise direction. Now fold your right hand fingers, curl your right hand fingers in the direction of current, and the extended thumb that indicates the direction of magnetic field. Now in this case the direction of magnetic field is representing along the positive x-axis. Suppose if we take that along positive x-axis, so it is representing in this direction. But I want to write this at point O. So we need to draw that direction at here. So this is the magnetic field direction due to coil Q. Similarly, in this coil, the magnitude of the magnetic direction at that coil at point O, that is exactly opposite. Now in this direction, so it is acting in this direction. Now to find the resultant magnetic field at point O, so let's find the magnitude of the magnetic field due to coil Q. So the magnitude of the magnetic field due to coil Q, magnitude only. Since O is along axial point, so we can write this formula mu naught n I a square upon 2 into a square plus x square whole power 3 by 2. So here a equal to radius and x equal to location of the point. But given problem, given a equal to radius equal to small r, and the x is also, the O is midpoint of 2r. So this is 2r and O is midpoint of 2r. Therefore, the x equal to, here I can take r itself. Now substitute these two values in the above expression. And here number of turns, they do not mention any number of turns n. So we can take that, let the n equal to 1 is the number of turns. So the magnitude of magnetic field, so modulus of BQ equal to mu naught in the coil Q, the current is 2I. So mu naught 2I times R square upon 2 times R square plus R square whole power 3 by 2. Now let's simplify this. Magnitude of the magnetic field due to coil Q, so here 2 gets cancels and the expression remaining terms mu naught I times R square upon, this becomes 2R square whole power 3 by 2. Okay, let it be equation 1. And similarly, if you find the magnitude of the magnetic field due to coil Q, sorry, coil P, so that is also same formula, mu naught n I a square upon 2 into a square plus x square whole power 3 by 2. Here a equal to radius r and x is also, the point O is at equal distance. So here also the x equal to r. And n equal to number of turns, let me consider 1, and current I, the current I itself, I equal to I only, the current is I. Now substitute and write the expression modulus of magnitude of the magnetic field at the B. So mu naught I times R square upon 2 times R square plus R square whole power 3 by 2. Therefore, let's further simplify. Mu naught I r square upon 2 times 2r square whole power 3 by 2. So this is the, let it equation 2, I think. So this is equation 2. Yeah. Now here we can see these two magnetic fields are acting opposite in direction. So when they both are acting opposite direction, to get the resultant magnetic field, the resultant magnetic field equal to, we need to subtract magnitude of magnetic field due to Q minus magnitude of the magnetic field due to P. So this gives the vectors subtraction. Then we can get the resultant magnetic field at that point. Since magnetic field is a vector, it is acting oppositely at the same point. Now let's subtract for the resultant magnetic field be equal to magnetic field due to Q minus magnetic field due to P. Now if you can write that mu naught I r square, mu naught I times r square upon 2r square whole power 3 by 2, that is 2r square whole power 3 by 2 minus mu naught I r square upon 2 times 2r square whole power 3 by 2. So let us simplify this. So mu naught I r square upon 2r square whole power 3 by 2 is common factor. I get it here 1 minus 1 by 2. Now if you can take the LCM, you can get that 1 by 2 again. So mu naught I r square upon 2r square whole power 3 by 2 of 1 minus 1 by 2, the LCM equal to 1 by 2. So this is the final expression, the magnitude of the magnetic field. Or if you can try to simplify further, since r square is there in the numerator, you can try to cut it that. So that is also possible if you can do further simplification. So anyway, I am leaving it here. The final magnitude of the magnetic field. And where is the resultant direction? So here the resultant direction is pointing towards to the Q. Therefore, the direction is pointing towards Q, or it is pointing towards positive x-axis or I cap, anything you can take it, or simply I can write that I cap.